Welcome back, Physics 30. So today we're going to go over assignment number 2. It's going to be weird because every time I open my mouth wide enough, I cast a spell. So just kind of ignore that every once in a while. My mouth just opens too wide. All right. So we want to write the decay reaction for the following transmutation. Show all the subatomic particles being produced. So that includes neutrinos, antineutrinos, gamma particles, positrons, electrons, etc., etc., etc. I might change this here, just change to a pirate. Okay, yeah, so here's my nice little pirate app. All right, so what's this decay happening here? So Ra, which is radium, decays into Rn, which is radon. Okay, yep. Let me get my pen out. So I'm going to write this out. Comes R. So 86. I've lost two things on the bottom here. So I have a little 2 over here. What else? On the top here, I've lost 4 things. Oh, so this is just alpha decay. And this is going to release the gamma radiation. So I'm just going to mention down here that this is alpha decay. Okay. Uranium, 235. So uranium is 92. You can just find that on the periodic table. Into thorium, which is 90, 231. So again, I've lost a alpha particle. Okay. Carbon, which is 6. This is carbon 11. Undergoes beta positive decay. So beta positive is a beta positive like this. There's a little positive there. So the bottom number's got to add up to 6. So this is going to be 5 here. 5 plus 1 is 6. The top number's got to add to 11. So 11. 5 is boron. Capital B. Okay? Because it's beta positive, I'm going to release a regular neutrino. And this, so remember, this is a neutrino. Okay? It's regular matter. This is a positron. You probably don't, it doesn't mention that you have to. You just show the particles, but that's what they are. Write the process for lead decaying into, or process of alpha decay of lead. So lead, Pb, which is plumbum, is 82, right? Where is it? Where am I? I believe it's 82. Yeah, it's 82. Okay. Undergoes alpha decay, so I've got to put my alpha first here. I'm going to lose 2 on the bottom because those had to add up to 82, so that's 80. And I'm going to lose 4, so this ends up being 204 on the top. So 80 is mercury. And a little bit of gamma. Estimate the energy being released here. So that's what the second page is all about. I got mercury, I got lead down here too. Okay, so mercury. What am I doing here? Mercury what? Mercury 204, lead 208. So the mass before, I'm trying to write small here, and the mass after. Oh, I have an alpha particle here too, so that's going to be very key. There's an alpha particle. All right, I have enough electrons altogether, so this could be a helium atom because I've lost 2 protons, but I kept all my electrons, so I got 208 somewhere in here. So this is a negative charged mercury, though. Let's go see. So lead 208. I wonder if I have that sheet loaded up on another page here. Okay, I do. Okay, so I'm not going to look down there, but I have it on my sheet over here on my other page here. So lead. Oh, I don't have. Oh, there it's lead 208. Yeah, I do have lead 208. It's kind of polonium's right in the middle for some reason. So 207.976652 atomic mass units. And then afterwards, I have mercury 204. I'm going to find that in here somewhere. Oh, I don't have mercury 204 on my list, do I? What? Kind of lame. I thought I would have mercury on this list. Well, I'm going to have to go find it. Just 1 second. Okay, so I found the mercury 204 number. I just searched mercury 204 online, went to the Wikipedia page for all the mercury isotopes, and I found mercury 204 there. That's where I found it. You guys probably just found it in Google Classroom because I just gave it to you. And the next one here is helium. It's an alpha particle. Remember, an alpha particle is the same as a helium nucleus. So you can say, or helium-4. And helium-4's mass is 4.002603 atomic mass units. I'm going to add those two together. No, I'm going to do my computer calculator here. Plus 4.002603. So I get a mass of something slightly lower than the other side, which makes sense because it's not going to be gigantically lower. I get 976.0969 atomic mass units. I got the 207 part there too. Okay, so the energy release is going to involve my mass defect. So I got to find my mass defect first. So I'm just going to go the mass before minus the mass after. So I'm going to take my number that I have in my calculator here minus that 207 number, 0.9, or the both 207 number, 6652. Okay, so I lose mass of negative 5.551 times 10 to the negative 4 atomic mass units. I'm going to change that into kilograms, times by 1.66 times 10 to the negative 27. But you don't have to worry about the negative there. 9.21 times 10 to the negative 31 kilograms. There's more decimals there. Just remember that that's just times in by that 1.66 times 10 to the negative 27 number. Okay, then I'm going to take that and put it over here, and the m is equal to, or e is equal to mc squared formula. So times that by the speed of light squared. Make sure it's squared. So I get 8.29 times 10 to the negative 14 joules. And that's a fine answer. I don't like communicating that way because that's weird numbers. I'm going to change it into electron volts by dividing by 1.6 times 10 to the negative 19. So I get 518,000, which is kilo electron volts. So divided by that number there. Cool. So we have a few more here. So write the complete process of the transmutation of phosphorus 30 to silicon 30. I think those are both in this question here. Silicon 30. Phosphorus 30 is there. Silicon 30 is there. Yep. Yeah, okay. So phosphorus 30 is P. And phosphorus is, where's phosphorus? Oh, phosphorus is P15. Okay. I don't know what I was looking at there. I don't know what my process was. Silicon Si is 14. So this is beta positive again. Oh, man. I like throwing the beta positive at you. We get the neutrino, because remember the bottom numbers had to add up to 15. I got a neutrino, and I get the gamma. What's the energy release? So I'm not going to go into the depth again, so you got to find this in your notes if you haven't done so already. Because this is beta positive, I have to worry about that positron the extra electron, and the atom. So the mass before, which is this phosphorus, that's in the sheet down here. Down here, you can see phosphorus 30 and the silicon 30, they're both there. And the electron are all the way at the bottom here. So got the electron masses. Surprised I didn't have mercuries in that list there, but I'll give you the mercury number later. So phosphorus is 29.978314 atomic mass units. And afterwards, we have silicon 30, which is 29.973. It's funny, there's more pieces in silicon 30 than silicon 28, but silicon 30 weighs less. What? No, I lost my train of thought. 770 atomic mass units plus the two pieces, the electron plus the positron. Okay, not a proton, but a positron. So I had to go down to my thing here and find the number for those. Cool. So the mass afterwards is going to be 29.97377. Oh, did I hit 7 twice? Yes, I did. Plus 2 times this 5.485799 number times 10 to the negative 4. Bam. So I get a mass of 29.974. So it is still less, even though I add those electrons on there, than before. So my mass defect, now the process is just going to be the same as what's before here. So my mass defect is going to be the mass before minus the mass after. I don't care if it's negative or positive. I know I'm losing mass. I just want the number. Yep. 0.0034368,402 atomic mass units. I'm going to change that into kilogram. Okay. Times 10 to the negative 30 kilograms, and then I'm going to change that. I don't know what this is. Change that into that. So times it by c squared. Times it by c squared. Okay. I'm going to get a joule number here. So I'm keeping all my decimals as we go. Keeping 3 sig digs as I write them down, but I have all these decimals in my calculator. And then I'm going to change that into electrons. Arr. That seems like a pirate thing to say. 3,218,000. So 3 million is a mega. So 3 mega, so 3.2. I don't have any proper sig digs. I'll just say 3. When in doubt, always go 3 mega electron volts. Not the biggest one we've seen so far, but that's okay. Yay, done. Yeah, we're done this one. I'll see you in the next video. Arr.